In this podcast, we're going to talk about a topic called direct variation. It's kind of uh, associated or similar to ratio proportion, so that's why we do it at this point. Uh, the direct variation method involves the modeling of a certain situation, and the building of the model involves finding a constant called the constant of variation. So what we're going to do is we're going to use direct variation as a means of introducing the notion of mathematical modeling. Now, to begin this, we're going to need to know how to do some translations from English into algebraic form. And the language will go like this. The first one says y varies directly as x. Now, how do you say that? What it means is if you double y, you double x, or if you double x, you double y. That's what direct variation means. The two variables act in the same basic direction. So how do you translate that into an algebraic equation? Well, if you see the English phrase y varies directly as x, the algebra translation for that is y equals k times x. This k is what we refer to as the constant of variation. And every one of the translations you're going to see always starts off y equals k. Now, it doesn't have to be y. You know, if it was temperature, you could say T equals kx. But we'll just be using y here as we set up the basic rules. The second one we want to talk to you about is just a different way of saying y varies directly as x. The other way that you could say that is y is directly proportional to x. The translation would still be y equals kx. Now, suppose the two variables don't act in the same way. Suppose if you double x, you cut y in half. Then we call that inverse variation. We would say y varies inversely as x, or y is inversely proportional to x, and instead of having y equal k times x, we'd have y equals k divided by x. And that would produce a situation where when x got twice as big, y got twice as small. The third one we do is really kind of an offshoot of the first one. It says y varies jointly as x and z. I don't use that very much, but I threw it in here because it's in most books. And we would say y equals kxz. So varies jointly as x and z is the same thing as saying y varies directly as the product of x and z. And then that would give you y equals kxz also. Or you could say y is jointly proportional to x and z, or y is directly proportional to the product of x and z, and both of those would give you again the same translation. So let's just see how to do a couple of translations with different variables. In example 1, we say translate u varies inversely as the sum of t and w. So we go to the inversely translation. That's this one. Y varies inversely as x translates to y equals k over x. So the x goes in the bottom. Here we're not varying inversely as x, we're varying inversely as a sum. So I would write y equals k over the sum. Now the sum of what? The sum of t and w. So that would be t plus w. And that would be the translation there. Translate q varies jointly as w and r, and inversely as the square of t. So what we're doing here is we're putting two of these together. We're putting the varies jointly translation together with the varies inversely to form a single equation. Each time you do this, you're setting up a single equation. Don't think that this is two different setups. Q varies jointly as q equals k times. Jointly as w and r, k times wr. And it varies inversely as the square of t. Now the square of t would be t squared, as opposed to the square root of t, which would be written this way. So you kind of have to watch that. It's really easy when you're taking a test or something to get the square confused with the square root. So this is the square of t, so you're going to square t, and it's going to vary inversely as the square of t, so t squared is going to go on the bottom, and that would be your translation. Now, all this translating does is it gets you started in a problem. There are many more parts to a direct variation problems, and we'll see that as we work a couple of direct variation examples here. So let's come down here to the steps for doing a direct variation math modeling problem. And what I'm going to want you to do is do this in 4 steps. The first step is to read the problem and do a basic translation as we just did in example 1 and 2. Your second step is going to be to find the value for that k, that constant of variation. And to find that, you're going to need to be given a set of data in the problem with a value for every one of the variables except k. If k is the only variable that you don't know, and I've made a mistake here, I used a small k here and a big K here, but I mean for them to be the same k. If you have a value for every variable except k, as you'll see in the examples, that will allow you to solve for k. Now, step 3 is something that people don't normally do when they're doing these problems, but we're going to do it, and it's called writing the math model. And when I give you this on a test, this is going to be part of the test question. And what this is then is a mathematical representation of a certain physical situation. So to find out what happens in the physical situation, you don't have to actually set it up and do experiments. Once this mathematical model is set up, you can just use that model to tell you what would happen as you change values for the different variables. And then finally, we'll use that math model to answer questions about the system. So let's see in a practical sense how that works through this first example. It says, suppose y varies directly as x, and x is 15 when y is 4. What is the value of y if x is equal to, what is the value of y if x is equal to 4? Okay. First thing we need to do, it says, is translate. So step 1, I'll do the translation. Y varies directly as x. That's about as simple as it gets. Y equals k times x. Step 2 is find k. So I need a set of data that gives me a value of x and a value of y. And it says right here, x is 15 when y is 4. So I'll go ahead and put for y 4. For x I'll put 15. So if I divide both sides by 15, the 15's cancel on the right, and I get that k is 4/15. Step 3 says write your math model. Now up here where it says write your math model, it tells you exactly how to do it. It says use the result of step 1. So that's y equals kx. So I'll start that off. Y equals something times x. Use the result of step 1 with the k from step 2. In step 2 I got k is 14/15. So in here where k was in step 1, I'm going to put 4/15 here in step 3. And now this is called the math model of the problem. Now once you've established your math model, y equals 4/15 x, you can now answer questions. The question asked is, what is the value of y? So we're going to find y. If x is 4, so I'm going to come in here to 4/15 times x, and x is 4, so y is 16/15, or you might say 1 1/15. Either one of those is a good answer. And that's an example of going through all 4 steps of a direct variation problem. Now let's take a look at a more complex example. See if our can't get access to the good clicker down here at the base, so I'll just do the best I can with it. Now here's a pretty complicated example problem. It says, if the force F between two objects varies directly as the product of their masses, m1 and little m and capital M, and inversely as the square root of the distance d between them. Okay, the force between two objects varies directly as. So I'll start off F equals K. Now guys, in every problem you do, it's going to start off something equals K. If it doesn't start off that way, you're automatically wrong. You need to have your constant of variation. Now it varies directly as the product of little m and big M. So it's going to be K, little m, big M. And it varies inversely as this time the square root. Now we didn't have that root before. This time it says, and inversely as the square root of the distance d, so I'll take the square root of d, the distance d between them. So there's my translation, and that is step 1, translate. Now step 2 says find K. This time it's going to be hard, because I need to find a set of data that has a big M in it, a little m in it, a d in it, and an f in it. So let's see if we've got such a set. It says F is 2800 newtons, so I'll put F equals 2800 newtons. When M is 60 kilograms, little m 60 kilograms. Big M is 100 kilograms, so there's the masses, big M and little m. And the distance between them, now this is a little bit confusing here, because it says 64 times big M. Well, that's just because I didn't have this separate symbol for meter and I didn't want to write it out. All that means is the distance between them is 64 meters. So I'm going to use a little m there instead of a big M for meters. In fact, I'll just write out meters. So I do have a set of data that has a value for F, K, M, and D. That's F, little m, big M, and D. So that's every variable except K. That means I can now find K. So I'm going to go ahead and plug into number 1. For F, 2800. K is what I'm looking for, so I won't be plugging in for that. For the little m, 60. For big M, 100. And over the square root of D over the square root of 64. Square root of 64 is just 8. So I'm going to just scratch out the square root of 64 and put 8 in its place. Well, let's see. I've got two terms here. The common denominator is 8. So I'll just multiply each term by the common denominator. So 8 times 2800 is equal to K times 60 times 100. And I'll divide both sides by 60 times 100. And the 100s and the 60s cancel on the right, leaving me with K. On the left, you could just pop that into your calculator if you wanted to. I'm going to do some canceling though. I'm going to cancel the 100 on the bottom with 100 on the top. So now I have 8 times 28 over 60. Let's see. If I do a little bit more canceling, I've got a 4 on top in the 8. So I'll cancel that and call it a 2. And I'll cancel into the 60 and call that a 15. So I'm just going to leave it that way. I'm going to say 56 over 15. You could simplify that in some other way. You could change it to a decimal or something like that. So now step 3, I'm going to write my math model. Now the math model is step 1 exactly. The only thing I'm going to do, the only difference between the math model and step 1 is that number 56 over 15 is going to go in for K. So I'm going to write my math model this way. F equals 56 little m big M over 15, there's my 56 over 15, square root of D. Notice everything except for the 56 over 15 is exactly the same as step 1. And now that's called step 3, and now I'm able to answer my questions using my math model. So the question says, what is the force between them? So apparently the them means we're going to stick with the same two objects. So that means little m is still going to be 60. Big M is still going to be 100. What is the force between them when the distance is increased to 100 meters? So what they're asking us to do here is find F. What is the force between them? Find F when Little m is still going to be 60. Big M is still going to be 100. And D, this time, is going to change from 64 to 100. So let's go ahead and plug in. F is equal to 56 times little m, which is 60, times big M, which is 100. All of that over 15 times the square root of D. That's the square root of 100, which is the same as 10. Well, now let's see. That opens up some possibilities. I could cancel this 10 with this 10, and that would leave me a 6. So that would make things a little bit easier to work with. What else could I do? I see a 5 here I could get rid of. But let's go ahead and do it over here so it doesn't get too crowded. I'll do 56 times 6 times 100 over 3 times 5. 15 is 3 times 5. So I'll cancel the 3 into the 6 and get a 2. I'll cancel the 5 into the 100 and get a 20. So this is just going to be 40 times 56. I'll put that on my trusty calculator. 40 times 56. And I blew it. 40 times 56 is 2240 newtons, because we were doing our force in newtons. So there is our answer, and there is our 4-step procedure for doing a direct variation problem. See you in the next podcast.